Does the theory predict anything different from quantum mechanics that would be, in addition to the test you've already mentioned, that would kind of prove the validity of the reverse wave theory?
Well, allow the distinguishing, one thing predicts, one theory predicts one thing and another something different.
Yeah, where it predicts something different.
I had thought that the right EPR experiment would detect the difference, but I've convinced myself otherwise. I can't think of any experiment where they actually predict something different. But again, the only way you can make the forward wave theory work is by embracing contradictions, like the waves going, narrowing the width after the waves go through the interferometer, affecting what happened earlier, or something like that. With this theory, there are no such contradictions. And to me, that's what you mean by explaining something. You make a hypothesis and you test it. And the test means, does it explain everything without contradictions? To explain something with contradictions is a contradiction. That's not what you mean. Back there.
Yeah. Is there any relation between the reverse wave theory that you described and the advanced wave reverse time theory that Kramer described about 10 or 12 years ago?
Yeah, well, that's what I indicated earlier. His reverse wave theory takes the forward wave, which is spreading out from a source, and then time reverses it. Well, the pieces of that time reversed wave are coming together, and they have to be mutually coherent when they arrive at the particle source. You'd need something non-local to understand how all those separate pieces end up being exactly right to end up in phase when they get to the source. Plus, there's no local way to understand how a particle could follow such a reverse wave, because the wave continually has to choose which branch to go into as it goes along, or the particle does. With reverse waves, the branches are coming together, and the particle only has one choice, which can be explained locally. I think that Kramer's explanation, it's just a reformulation of the contradictions, in effect. It states the problem of quantum mechanics in a different way, but it doesn't really resolve it. That question back there?
Yes. I know that reverse time sort of bothers you as being non-physical, but have you looked at a reverse wave reverse time theory and see if that's a simplification?
No, because that's exactly what I'm trying to get away from, is that sort of thing. If I had a few minutes here, I could show you how the Feynman propagator, which involves supposedly negative frequency waves going backwards in time, actually everything still goes forward in time. Time reversal contradicts what you mean by time.
Well, I'm not sure it would. In a reverse wave, reverse time theory, at least particles would always move forward in time, which is what we observe. So,
well, all right. As just a half of the explanation I intended to give. If you imagine a negative frequency electron wave, say, that means the flux is going one way and the wavefronts are going with it. Now, if you put that into a Feynman diagram, you know what I should do is look at a slide. I need slide 14.
While you're changing slides, I'd just like to make a comment.
Yes.
Kramer's theory is a self-consistent interpretation
That's
of
the one.
quantum mechanics because it reverses time and space. Any wave equation obeys reciprocity, which says that if you have a solution of any wave equation, Maxwell, Schrodinger, and you reverse both space and time, you get another solution. If you just reverse space and don't reverse time, the result is not a solution of any wave equation, okay? So the problem here is that you've never written down a wave equation for us to look at to point out this flaw. This is really just a semantic shell game that really hides the underlying problem. You want to reverse space but not time, because if you reverse time it leads to acausal effects like Kramer's theory has. But you can't do that and have a wave equation, have a theory of waves. Even though this is a theory of waves, there's no wave equation in any of your presentations or in your paper. How can you have a theory of waves without an equation?
The equation is the same. It's the Schrodinger equation.
Then this is wrong. You cannot reverse space and not reverse time and get a solution of Schrodinger's equation.
Again, I'm not reversing space and reversing time.
That's what I'm saying.
What I'm looking at is a wave. I'm looking at a wave that would be exactly like a quantum wave emitted by the
Such
detector.
a thing does not exist. If you reverse space
it does.
and not time, you don't have a solution
But
to
see,
any
I'm
wave
not
equation.
reversing space. I'm
This
not
is,
reversing space.
you're reversing the motion in space,
No.
yes?
No,
No, I'm not.
you're positing a different.
I'm positing space is the same and time is the same. All I'm saying is the relevant wave is actually being emitted by the detector, not by the source. I haven't done anything to space or time.
Well, it doesn't work on astronomical distances. Because imagine a photon being emitted from a supernova, which is going to arrive here 3 days from now, right? You have a detector sitting here, it sees the photon. And when does it emit the wave to go back? So 400 years later, there is nothing there. The supernova is gone.
Well, as I say, the fluxes are around all the time. So you can have a particle photon following it. Because we live in a Lorentzian universe, no matter what it's following, coming from wherever, it'll always travel at velocity c relative to anybody. Now, it turns out,
No, the detector was not created till a week ago. How is it going to...
Whatever time.
400 years.
Doesn't matter. He's asking.
doesn't matter, any time before. It turns out that as the photon changes, you can, I'm not sure if I can get to it today, but you can give a good argument that will show that when you do finally see the photon, as it jumps onto the final wave that comes from you, the state when it arrives at you is exactly what it would have been if your wave had in fact gone all the way. In fact, it doesn't, but it ends up being the same. All right, question right here.
Yes, I think it follows up the previous question, if I may just say quickly.
Yeah.
You did that slit experiment. It was a very nice experiment you showed. And it indicated that indeed, if you look at these waves coming to the detector, then those detectors send these waves back to the source and like a decay. And that allows the particles to follow a particular path which was geared for going that direction, if I understood your explanation.
Well, there's no wave going forward now. It's not.
Going from the detector back to the source.
Yeah, that's the only right one.
Exactly. Now, the question I have, since this is not instantaneous, it goes with the speed of light, what happens in that interval if the media changes? Then it just looks like kind of a difficult scenario that constantly you have to gauge yourself with the media which is changing in order to create the route for the particle to take the right path. So how would that come into the perspective?
Well, what happens is if the detector moves or something changes, then the waves become those emitted by the new object, and they will travel toward the oncoming particle. And when they arrive at the particle, it has to change. It has to jump to following one of those new waves. And then when it follows the new wave to the new detector, and it'll be seen. I mean, we saw an example of that with Bell's theorem.
Coming back and ultimately detecting looks to be a little bit dependent on the scenario of the media itself.
Sure, if you had a bigger double-slit experiment, it would be a bigger time period.
Well, no, I'm really more changing media. If the media in time span changes, its properties, the epsilon changes, or something changes in the media, how would then
well,
you see this, the beacon signal coming back might see different routes, so it's not true reciprocity in instant sense, because now the media has changed.
Well, the flux will always travel at velocity c, even if you do put a medium there. The problem is if you have a medium, there's going to be an interaction with the fluxes in the medium. I haven't actually gotten to the point of, in effect, solid state type analysis here. My sense is that it will carry over in a straightforward manner, that block waves will become another kind of these elementary waves, and phonons will follow them in the reverse direction, and you'll get an almost identical theory to what we now have. Whether those block waves would involve some forward and back type motion that would make it look slower, I'm not sure. I haven't gotten to that point yet. Mainly, I just want at this point to show that the problem of quantum mechanics is solved by doing this, and you get relativity, and you get a way to fully picture these Feynman diagrams. Picture them first for the waves, and then also the way the particles follow them.